Hello, so in this video I'm going to be talking through the method of variation of parameters, and I put in brackets this is the proper method because the methods which we looked at up to now of solving the non-homogeneous second order differential equations. So non-homogeneous just basically means the right hand side is not zero, okay, so it's got something involving t on the right hand side. Basically the variation of the method of undetermined coefficients is the method that we've looked at of solving it. And that basically involves, we basically find the solution to the homogeneous part. We solve the solution to the homogeneous part, okay, and we call that YC. We call that YC because it's the complementary solution, okay, and then we basically build the solution to the non-homogeneous part. So the solution to this part, where the right hand side is not zero, by basically finding some particular solution and saying, well, okay, the general solution must be the complementary solution, so the solution to the homogeneous part plus the particular solution. So the particular solution, we have to basically make a guess based on what the right hand side looks like. Okay, so effectively it's like a guess. Now this method, the method of undetermined coefficients, is fairly limiting because for a start we need that a and b, these coefficients here, they must be constant. Okay, they can't vary at all. They have to be constant values. Okay, and we're also limited by what the right hand side looks like. Okay, but so basically we want either an exponential right hand side, a sine or cosine right hand side, or a polynomial right hand side. Okay, or multiples of them. Okay, but if it's anything other than that, then we're pretty stuck, basically, and we can't use method of undetermined coefficients, okay? So, for example, so we can't use method of undetermined coefficients. So what do we have to do? So there is another method that exists if we can't use method of undetermined coefficients, and it's called variation of parameters. And I put in here the brackets, the proper method, because it's the proper method because it actually extends to higher orders as well. It's actually the correct way of doing things. And it kind of covers all of the cases. So, it doesn't matter whether these are variable or not. So if they're variable coefficients, then we use variation of parameters, okay? And, like I say, it extends to higher orders as well. So, we only look in this course at second order differential equations. We only look at second order differential equations in this course. That's the highest order that we look at. So we also look at first orders as well. But, we don't look at any orders which are higher than that. So, but yeah, say like if we had a fifth or sixth or seventh order differential equation, then we would use variation of parameters. It extends to all of the orders. Okay, it's just going to, as we increase the order, then they become harder to compute. I talked about that before. That differential equation solutions. Hello. So in this video, I'm going to talk you right. So as we add more dimensions, so as we consider differential equations with more dimensions, they become difficult to solve. Okay, but anyway, that's beside the point. So this variation of parameters is what the idea is. And just like method of undetermined coefficients, we do need to consider the solution to the homogeneous part. Because if, the solution to the homogeneous part compared to, what you're considering now with the non-homogeneous case is really, really easy. Effectively just form something that looks like a quadratic out of the homogeneous part and basically look for a solution of the form y equals e to the rt. Okay, so you can easily form the complementary solution. Okay, we call that complementary solution, and then we basically then form the solution to the non-homogeneous part from that. Now, the thing is, the general method of variation of parameters requires no kind of detailed assumptions. So in other words, we don't have to make any guesses based on what the right-hand side is going to look like. So in other words, we don't need to find some particular solution based on what the right-hand side is going to look like. So that's one bonus. We don't have to make any kind of guesses as such. We do have to make a few assumptions, but we don't have to make any guesses just by blind guesses, just by looking at what the right hand is going to look like. But it does involve integration, and sometimes the integration can turn a bit nasty. But other than that, we're not really worried. So this is kind of like the proper method of doing things. So I think the best way of seeing how this works is by using examples. So here's my example. It's a non-homogeneous second order differential equation, okay? And we can't use method of undetermined coefficients here because, well, although we've got constant coefficients, because effectively there's a zero y dash hiding in here, we don't have to worry about. So that is a constant. There's a constant there and there's a constant there. So constant coefficients. So that ticks the box of that we might be able to use undetermined coefficients. But look at this right hand side. That's where we're let down because we've got effectively this is 3 over sine t, that's what cosec is equal to, it's 3 over sine t. Well, remember, we can only really use method of undetermined coefficients if it was like 3 sine t. Yeah, because it's 3 over sine t, effectively it's written as a quotient, we can't use method of undetermined coefficients. Okay, so therefore we're going to have to use this variation of parameters. So first things first, we need to solve the corresponding homogeneous equation. So the corresponding homogeneous equation is like this. So plus 4y, and we just set it equal to 0. Effectively, we just ignore the right-hand side. Okay, so let's have a look at this. We solved the corresponding homogeneous equation by doing. We've basically formed the characteristic equation. This is r squared plus 4 equals 0. Let's do a little bit of rearranging then to find what r is equal to. So this becomes minus 4. So therefore r must equal the square root of minus 4. R must equal the square root of minus 4. We're taking the square root of negative numbers. Therefore we know it's going to be an imaginary root. Okay, so this is going to become, this is effectively the same as doing the square root of 4 times minus 1. Okay, we can break it up into then 2 square roots, and we know that the square root of minus 1 is just going to be I. What's the square root of 2? Well, it's going to be plus or minus 2. It's going to be plus or minus 2. So now we've got r is equal to plus or minus 2. So let's let r1, let r1 equal 2i, and let's let r2 equal minus 2i. Okay, so therefore, remember, we're guessing a solution of the form. When we've got a homogeneous case like this, we guess a solution, or we look for a solution of the form e equals e to the rt, y equals e to the rt. Sorry, I think I said e equals, y equals e to the rt. So therefore, that means that y1 is going to be e to the r1 times t. Well, r1 is 2i. R1 is 2i, so I'm just going to write like that, so 2ti, okay? And then r2, or y2, is going to be e to the r2 times i. E to the r2 times t, so what's r2? It's going to be minus 2i, so I'm going to write it as minus 2 t times i. And what I'm actually just going to do is I'm just going to rewrite, I'm just going to be a little bit naughty and rewrite it like that. I'm not naughty because it's absolutely fine writing like that, but I'm just going to write it like this because it will make it clearer for you guys later on. Okay, so remember we're guessing a general solution of the form y equals c1 y1 plus c2 y2. Okay, so what's y1? It's going to be e to the ti. In actual fact, I'm going to leave it, I'm going to try and expand these things out for the time being. So I'm going to try and find out what these things are, because remember it's just e raised to some imaginary number. So, you know, if you remember e to the I theta, okay, is, we can expand this out as cos theta plus I sine theta, okay, I sine theta. So therefore I can expand this thing out before I go any further. So y1 equals e to the 2ti, so I can say that this is going to be cos, effectively my theta is 2t, effectively my theta is 2t, so it's going to be cos 2t plus I sine 2t. I sine 2t. Okay, so that's that expanded out. What's y2 then? So y2 is going to be e to the it's going to be cos 2t. It's going to be cos 2t. Yeah, because that's my theta. Minus now, because that minus I corresponds to a negative, minus I sine of 2t. Now remember that, you know, the reason why I wrote it like that is then hopefully you can see why that should be a minus. It's not really strictly speaking a full proof as such, but I've written it like that because these two things should be conjugates of each other, right? Because you've got plus 2ti and then minus 2ti, so they should be conjugates of each other, so therefore that should correspond to a plus and minus in there. So that's the reason why. Okay, so now what I want to do is I want to basically form my general solution, and I'm going to be a little bit sneaky here. I'm going to say, well, okay, y is going to be k1 y1 plus k2 y2. So let's have a look. So what's k1 y1? So y1 is just going to be that thing there. K1 is just going to be that thing there. So y1 is going to be that thing there, sorry. So k1 times that thing there. So if you do that, there we go. K1 times that thing there, plus k2 times y2, which is going to be that thing there. That's that thing there. So let's have a look, see if I can squeeze that on. There we go. So this is k2 times that thing there. Okay, cool. Then I'm just going to expand this out and try and do a little bit of simplification. Okay, so this is going to be k1 cos 2t, k1 cos 2t, plus I k1 sine 2t. So I'm just expanding through, just expand that bracket out. Now let's expand this bracket out. So we've got plus k2 cos 2t minus I k2 sine 2t. So let's have a look and see what we've got here. So I'm just going to collect together like terms. So I'm going to collect together the causes and the sines together. So effectively what I'm going to left up with is we're just going to take out a cos 2t. I'm going to take out a cos 2t, okay, and I'm going to end up with a sine 2t over here. So I'm just going to basically take out a k1 and a k2. Okay, so k1 plus k2. So that's the same as k1 plus k2 cos 2t, plus then what about the sine? So I've got I k1 minus I k2. minus I k2. Okay, now this is just going to be some constant. Okay, it's some constant plus another constant, so I'm just going to call that c1 cos 2t, so therefore y is equal to c1 cos 2t, and this again is just going to be another constant. Okay, albeit it's going to be imaginary, but it's still going to be some constant, so I'm just going to call it c2. Okay, so c2 sine 2t. Okay, so this is basically my solution to my homogeneous equation, so it's my complementary solution.